as we wait for a few more people to come into the lecture. Yeah, so as we're waiting for a few more people, I will be starting the whiteboard. Just give me a minute. Right, so students, it's oh, I have a couple of more people now in the waiting room. So Tejas and Yuvraj just joined us. Right, so here's where we begin today's lecture. So hope all of you guys have been doing fine, and somehow you're getting over the frustration of the extended lockdown. I know it's very difficult for all of us, including me, but what can we do? I mean, in the meantime, we can just make sure that our studies are going as smoothly as possible, and that's what is the aim for us here. Okay. So I hope all of you had a chance to go through the sheet that I sent you, the worksheet with some examples, etc. And to begin with, I will be solving some of the questions from that. So if you have the worksheet with you, if you can just go through the questions once, and we'll discuss a few of them. So, I mean the questions at the end, the worksheet questions, not the solved examples, which I'm sure most of you would have understood. So I think the first question was pretty simple in the worksheet. The first question is just relating about, it's about a runner who runs 2 kilometers in 5 minutes and then takes a U-turn and walks back to the starting point in 10 minutes. So it is just to illustrate the difference between distance traveled and displacement, and also about average velocity and things like that, average speed, average velocity, etc. So you should be able to answer that question properly. Okay. Second question is about, again, a particle moving from a certain position on the x-axis to from 5 to -7 and back to +2 and all that. So again, it is a type of question we were discussing last time. It's again got to do with the difference between distance traveled and displacement and things like that. So I think you should not have any difficulty with the second question either. So I mean, I think most of these questions are pretty simple. Now let's move on to question number 4. Okay. So question number 4 is where I will start with. Okay. So let's look at quick review of the homework assignment. So I will also send the answer keys of these questions so that you can verify your answers. Okay. But in the beginning, I did not do that because I wanted you to try out the questions and make sure that your answers are correct, before you. So that's right. So anyway, so let's look at the 4th question in this. So the question says that there is a particular particle which starts from the origin, goes along the x-axis to a point 20, 0, and then returns along the same line to the point -20, 0. So to find the distance and displacement during this time. So I mean, through the 4th question, you will also get an idea how to solve the 1st, 2nd, and 3rd in case you haven't, because they're all questions of the similar type. So let us say this point over here is our x equal to 0. Okay. This point is our +20 along the x-axis, which is in meters, and somewhere here we have -20. So what happens is that our particular particle or body or whatever, let's say it's a person or something, they are present here at time t equal to 0. Okay. Then they travel along a straight line, okay, along the x-axis. So at a certain time, let's say t equal to t1, they reach over here, having traveled during this time along the straight line like this. Okay. And then what they do is after that, let's say we use a different color to show, after t1, they are traveling along this direction till finally at some time t2, they reach over here, where obviously t2 is greater than t1. Okay. So during that time, they are from t1 to t2, they are traveling along this direction, whereas from 0 to t1, they are traveling along this direction. Okay. So the question is very simple, but there is a small assumption while solving it. Okay. So we have to calculate the distance traveled, displacement, etc. So just before we get into the exact values in the question and all that, let's just understand what the assumption is. That the assumption here is that during the motion from origin to the point plus 20 comma 0, okay, or that is during time 0 to t1, okay, the direction of motion is always along positive x-axis. That is what we are assuming here, is that the body does not turn during that motion. It does not take a U-turn any point of time. So the motion is not like this, that he goes like this, then turns back, then goes like this, then turns back. No, it's not like that. He goes in one straight line like this, from 0 to 20. Okay. And then again at 20 or at time t1, so this is the first assumption we're making. Then obviously at t equal to t1, okay, the body makes a U-turn. Okay. And then proceeds to this point, minus 20 comma 0, again without turning in between, without turning in between, this time from t1 to t2. Okay, so again that's the second assumption that we make, that when he's going from 20 to the point minus 20 now, going past the origin where he started, he's going like this. He's not going back and forth, back and forth. Okay. So with that assumption in mind, I think all of you can understand that if you talk about the displacement from 0 to t1, it will be plus 20. If you talk about the displacement from t1 to t2, it will be minus 40. Whereas if you talk about the displacement for the entire journey, 0 to t2, that will be how much? That will be minus 20. And all the answers are in meters. Because displacement is nothing but the shortest path or the straight line from the initial position to the final position. So if I look at the initial position being the origin at t equal to 0, I can see that at t equal to t1, where the body has reached, it's reached this position plus 20. So the displacement from 0 to t1 is just plus 20. But similarly, if I talk about the displacement from 0 to t2, you can see that he's actually gone from there to plus 20 and then back to minus 20. So his net displacement in the third part, 0 to t2, is actually minus 20. And similarly, his net displacement in the second part from t1 to t2 is again minus 40. So he's gone from plus 20 to minus 20. So that's the easy part. Now about the distance traveled. So we have to understand that distance is different from the displacement in the fact that it is the path length. So distance traveled. Okay. So that is where our assumption will come. That in between 0 and t1 he is not turning. In between t1 and t2 is not turning. It's only at one point of time t1 when he makes a U-turn. He doesn't go zigzag. So with that assumption in mind, let's say we denote the distance with the symbol d. So the distance traveled from 0 to t1 will be the same as the magnitude of displacement because he is not turned in between. Similarly, the distance traveled from t1 to t2 will again be the magnitude of displacement, which is 40 meters, because in between he is not turned. But the third part, when we are calculating the distance for the entire journey from 0 to t2, in that part you will understand that the distance is becoming different from displacement, because in this time interval he has made a U-turn in between. So now his distance is going to be more than his displacement. His distance is going to be the distance traveled first from 0 to 20, which is 20, and then from 20 to minus 20, which is another 40 meters. So his total distance traveled will be 60 meters, okay, which should not be given with any algebraic sign. Should just be given as a magnitude. So his distance traveled in the third case for the entire journey will be 60 meters. Okay. So I'll just minimize this for a moment and take a look at this, but I'm sure all of you got this question correct. So now I will move on to, I think, the sixth question, because fourth question is again something I would assume is pretty simple for you to solve. Sorry, the fifth question is easy enough for you to solve. Fourth question is what we just done. So in fifth question, okay, we finish writing this down first, then we'll discuss a little bit about the again, it's a little bit word play. The physics part is very easy. You have to just understand that what is the assumption the question is asking you to do. So people, I hope this is clear, and Just checking for your messages. Yes. Yes. So I'm coming to the sixth question, guys. That's what most of you are asking about. Okay. So I think we are in a position to move on now. So I will just briefly explain the fifth question once, and you'll be able to solve yourself. Whereas next we'll be solving the sixth question. So I'm just reading out the statement of the fifth question to make one point clear about it. It says that it is a 260 kilometer. There's a word missing over there. It should say it is 260 kilometers. Sorry, it's fine. It is 260 kilometers from Patna to Ranchi by air and 320 kilometers by road. Okay. Now, typically, if you look at flight paths, you will see they are mostly straight lines between cities. Okay. Unless there are some extreme conditions like winds and all that, which are causing the straight line path to be unfavorable to the path. Okay. In order to save fuel, if we assume that wind speed is not a big deal, which we'll assume over here, we have to assume that between wherever Patna is, let's say Patna is here and Ranchi is over here. This is the fifth question. So the flight path will be a straight line. So that's what the first line is saying, that the flight path is a displacement of, or the flight distance is this much, 260 kilometers. That means the actual displacement is of magnitude 260. Whereas by road, if you go from Patna to Ranchi or whatever, you see that roads typically wind a lot. So that becomes the path like this. And that distance is given to us as 320 kilometers. So you have to understand that even if you go by road, your displacement is going to be 260 kilometers, but your distance traveled is going to be 320 kilometers. But if you go by aeroplane and assuming that the flight path is a straight line, not taking any wind into account, then our assumption will be distance will be equal to displacement. So that is about it. So that's very simple. Now moving on to the sixth question, the one we've all been wanting to look at. Okay. Yeah. So sixth question, I can see why some of you are asking for the clarification of it. So let me see. So it says the position of a particle depends on time according to this equation. Okay. So the position x of a particle depends on time t according to this equation. So this equation is given to us, x is equal to 1 meters per second square into t square, okay, minus 5 meters per second into t, okay, plus 1 meter. So this is some information that is given to me. So you just think of it like a quadratic function. It's like x is equal to some constant alpha into t square plus some constant beta into t plus some constant gamma or ABC of it, where alpha is a constant which has a unit of meters per second square and value of 1. Because see, alpha will be multiplied by t square, and on multiplying alpha by t square, it should give me the same unit as x. So that is why alpha's unit has to be meters per second square, because t is in seconds. Okay, so here t is in seconds and x is in meters. That becomes the inherent unit. Beta's value you can see is minus 5 and its unit is meter per second, because beta into time should give me the unit of length, which is meters. And similarly, gamma should have the same unit as the length. So that is why it is given to me in 1 minute. So this is another way of expressing the same. This equation is giving me the same information as the original. Whatever information this equation is giving, you can think of it. Now, based on this, we have to answer certain questions. So let's see what we have to answer. We have to find the displacement and average velocity from 3 to 4 seconds, and find a general formula for displacement from the time interval t to t plus delta. Okay, so let's look at these two and find the instantaneous velocity at any time. Okay, so let's start with finding the distance and displacement from 3 to 4 seconds. Okay. So for that, let us understand the behavior of x. The behavior of x is something like this over here, that you can see that, for example, if I just see at various different times, just to try and understand what the question is saying. No, I'm not. To answer your question, but I don't mean that alpha, beta, and gamma are assumptions. I'm just saying that you can express the equation in the form of a quadratic function. That x is alpha t square plus beta t plus gamma, where the question is in fact giving us the values of alpha, beta, and gamma. So they are not assumptions on my part. So the values of alpha, beta, and gamma are according to what the question is giving me. They are not really assumptions on my part. The question is giving me this information. So that is showing me that x is a quadratic function of time, where the coefficients of t square t and the constant value, they are nothing but 1, -5, and 1. Right? So that is what I mean by saying this. Okay. Now, before we get into the problem, let us try and understand the behavior of the particle. So let us see that at t equal to 0, what is the value of x? Just substitute time t equal to 0. So it's nothing but gamma or plus 1. Then let us understand at t equal to, let us say 0.5 seconds. What is the value of x? Just check how much will be the value of x. So see, the first term 1 into t square will give you plus 0.25. Okay, because t square. Then the second term will give you minus 5 into t. So that is nothing but 5 into 0.5. So that is minus 2.5. And the third term will give us 1. See how much we are getting finally? We are getting minus 2.5 plus 1, that's minus 1.5. So it will become minus 1.25. You can see it is minus 1.25. So something very interesting is happening over here. The particle was at 1 meter initially, and at 0.5 seconds, it's actually gone to minus 1.25 meters. Okay. And we'll understand in a minute why this is happening. Then again, let's check the motion of the particle at t equal to 1 second. Then let's again check at t equal to 2 seconds. Then let's again check at t equal to 3 seconds. And let's again check at t equal to 4 seconds. And I'll stop at 4 seconds because they have asked me in the first part to find the displacement and distance in this part of from 3 to 4. The earlier part I was just going to analyze the question a bit. It was not really necessary in that time, but I just wanted to get a feel for the question, so I did that. So first of all, I'd like you all to sit and calculate this table for me. What are the values of x at these different times given this function? Okay. So just substitute the values over here. I will be putting them up. So x at t equal to 1, how much that is? X at t equal to 2, how much that is? X at t equal to 3 seconds, how much that is? And again below x at t equal to 4. So just substitute the values of time. So I'm just doing the calculation on the side over here. You can do it. So for example, at 1, you can see it is becoming 1 minus 5 plus 1. It's becoming minus 1. Then at 2, it is becoming 4 minus 10 plus 1. So it is becoming, interestingly, it's again minus 5. Yes. So again, it is minus 5. And then at 3, you can see it will become 9. Minus 15 plus 1. Like that, just keep calculating the values. Just a small correction. That's correct. That at t equal to 1, it is how much? It is minus 3. Then at t equal to, so that was 1. 1 minus 5. Then at t equal to 2 seconds, you can see it was this. Then at t equal to 3 seconds, again it is how much? 10 minus 15. So that's minus 1. Whereas at t equal to 4 seconds, you will see it will become 16 minus 20 plus 1. Correct? T squared, so that's 16 minus 20 plus 1. So that becomes how much now? That becomes minus 3. See, x4 is minus 3. If you analyze these numbers, you see something very interesting. Now, another thing you'll see is that if I calculate 2.5, anyway, that's not necessary here. So what is this pattern actually showing you? Let's plot this on the number line. So hope all of you are getting these values. Just double check these values. Hope all of you are getting them. Right. So now I'm just going to plot this information on a number line or on the x-axis. So let us say this is where our origin is. So where does he start from at t equal to 0? He starts from here. He starts from x equal to plus 1 at time t equal to 0. Then where does he reach at time t equal to 0.5 seconds? He reaches here. He reaches at minus 1.25 at t equal to 0.5 seconds. Then where does he reach at t equal to 1 second? So between this time, you can see he's going like this. Between this time, he's going like this. So he reaches minus 3 at t equal to 1 second. Then he goes further in the same direction, you can see. Because at t equal to 2 seconds, you can see he reaches minus 5. But then you will understand that he continues like this, goes somewhere here, and then returns back. So that is why he is back to this position at t equal to 4 seconds. You can see that at t equal to 4 seconds, he is back. Sorry, t equal to 3 seconds minus, he is back over here. And then, so he's coming back now like this. And then he's reaching again here at t equal to 4 seconds. He's back to x equal to minus. So I'm just magnifying this diagram a little bit, but you'll understand that in this diagram, I have just effectively plotted on the x-axis what I had answered earlier, what I had got earlier. So he is going, towards the negative x-axis from 0 till some time where we actually don't know this time because it's something in between 2 and 3. Because you can see that at 2 he was at minus 5. Then again at 3 he's back at minus 5. And now from 3 to 4 he's going to from minus 5 to minus 3. So in between 2 and 3 he must have turned his direction. So what we understand that at some time t, which is in between 2 seconds and 3 seconds, he or she, whatever, must have reversed direction. From negative direction to positive direction. So this is just, I've not done any mathematical analysis other than substitute the values and just get some coordinates at some particular time. And from that, I'm just understanding the pattern of the movement. I've actually not done any equation solving. I'll show you all these things by equation solving also. And that also becomes very important in our method of analysis. Okay? But right now, I just want you to pay attention to what, generally, just the values, what kind of information they give us when we are solving a question like this. Just the values of the different x's at different time, they are showing you a general trend, how the motion is happening. I don't know the value of this exact time yet, but I know just from the values that the trend is like this, that from 0 to something past 2 seconds, he was going backwards. And then from that time, which is something between 2 and 3 seconds, till 5 seconds or 4 seconds or whatever, he's now going in the forward direction. Okay. So this is the information I have. Now, why this information is very critical to me? Because in the question I have been asked between 3 and 4 seconds. So now you can see that between 3 and 4 seconds, what is happening? Is this direction changing? No, this direction is remaining constant. So that's why both distance and displacement will be the same, which will be the motion from minus 5 to minus 3. So that will be displacement will be written as plus 2 and the distance will be just written as 2 meters. So therefore you can see that between t equal to 3 seconds to t equal to 4 seconds, his or her direction remains stable. Direction of motion remains stable. fixed, okay, along the positive direction. So that is why we can say that distance traveled will be equal to magnitude of displacement, and the displacement will be equal to what? It will be the value of x at t equal to 4 seconds minus the value of t equal to 3 seconds. So that is going to be whatever our minus 3 minus of minus 5. Okay. So the displacement you can see is plus 2 meters. Okay, so the displacement will be answered with a positive sign, and the distance traveled will just become 2 meters. Okay. So this was a critical thing for that part of the question. Okay. So I'm just minimizing this for you to see this clearly again. Okay. But this is the final result that I've got by just analyzing the numbers very simply at different times. In fact, even that 0.5 was not required. I could just analyze it every 1 second from 0 to 4 seconds. And you can continue this analysis beyond 4 seconds also. It will give you some useful information. Now I will also show you this information in a different manner by using equations next. But this is just, you can say this is the most basic way of understanding the question. This is the most basic way of getting a feel of what's happening in this motion. Okay. So we have got the displacement, that's this much. We have got the average velocity we can now get as the displacement divided by time. If we were asked to solve the distance, we would have got that also, that's 2 meters. And if we were asked to solve for the average speed, that also we would have got as the distance divided by the time. Okay. So that is the part where we are solving for the journey between this thing, between 3 and 4 seconds. Okay. Now let's come to the next part of the question, which is asking the for the general formula of displacement from t to t plus delta t. Okay. So in that we don't have to do anything. We have to just, substitute the definition of what is meant by displacement. Okay. So people hope this part is clear to all of us. Okay. So I'm assuming that's all clear because my chat is also clear. Okay. Now the next thing is we want to find out the second part. We want to find out the formula for displacement from t equal to t equal to t plus delta t. You have to find this distance. Okay. So what is displacement basically? Displacement is change in position, or it is x final minus x initial. Okay. So in this case, what will be our x initial? It will be the value of x at time t equal to t. So that was how much? It was 1 meter per second square into t square, okay, minus 5 meters per second into t plus 1. So just to make this easier to look at, I'm just going to remove the units. Okay. You understand the units are already there. So xt, which is my initial value of x, is t square minus 5t plus 1. Well, it's understood that this t square is multiplied with a 1 meter per second square, and that 5 is nothing but in meters per second. Okay. Now similarly, in this interval of time, so what is my interval of time? My interval of time is t to t plus delta t. So that is why this will be counted as the initial time, and this will be counted as the final time. So that is why I have taken my initial as this. So similarly now, what will I take as my final over here? I will take my final as the value of the x coordinate at the time t plus delta t. So that will become what? Just substitute over here, instead of t in this equation, substitute this as what? T plus delta t. Okay, so my x final will become, instead of t plus delta t, so that whole square minus 5 into the time, so that is t plus delta t, okay, plus 1. So this is my final x coordinate, okay, and this was my initial x coordinate. So now my displacement is going to be what? Is going to be the difference of this. So the displacement in that interval is going to be the final value of x minus the initial value of x. So all you do is subtract these two. So you can see you have t plus delta t whole square minus t square. We can keep these two terms together. This minus this, minus 5 times, we can take common, t plus delta t minus t. Okay. And then the last term is anyway going to cancel out, 1 minus 1. the constant term is the same in both the equations. So 1 minus. But you don't need to write down in so much detail like I'm writing. You can just subtract this minus. So anyway, so you can see what is this term going to give us. It is going to give us 2 times t into delta t plus delta t squared. Okay? And this time is going. This term is going to give us minus 5 delta t. So our final answer is what? It is delta t squared minus 3 delta t. Okay. This is our displacement from t to t plus delta t. Okay. In this interval, this should be our displacement. So this is the tricky part, which was the answer for the second thing. How to get the displacement in a time interval from t to t plus delta t. It is like this. Okay. Where it is understood here that the displacement will come out to be in meters as long as we substitute delta t in seconds. Now the rest these coefficients take care of, because there's a 1 over here which is in meters per second square, and this 3 is coming from some kind of subtraction, which includes meters per second. So this is 3 meters per second multiplied by second, so it is in meters, and this is 5 meters per second. Sorry, this is 1 meter per second square into delta t square, so it's coming out in meters. That's why my s is in meters and my delta t is in seconds. So just take a look at this in the entirety and make sure the steps are clear, and you will understand that all I have done here is I have applied the definition of displacement. The displacement is nothing but final x minus initial x as far as the straight line motion is concerned. Now, a few lectures from now, we'll start to understand what is the displacement in a 2-dimensional motion or even a 3-dimensional motion. But as of today, we are sticking to just the motion along a straight line. So displacement is nothing but final x minus initial x. Okay, guys. So hope this simple thing is clear. Just take a minute to go through this. Now, I'll also explain the third part, and through the third part, we'll understand the question using a different method. All right, people. So I think this is good. Okay. So just checking for your messages again, if any. Yeah, we can use differentiation and all that. Okay. To answer your question, Aparna, and we can differentiate, but here I will be avoiding differentiation at the moment, because we will be studying differentiation in detail, and after that I will again explain to you how to use differentiation. But if you're aware of differentiation from the beginning, then you can always do that. Okay. Dhruv, you didn't get the last step from the second last step. Okay. So the last step from the second last step, it is just that displacement is final position minus initial position. So I've written the formula for x final, I've written the formula for x initial, and I've just subtracted the two things. So just this the final step is what all I've done in the final the second last step or whatever is that I have calculated this thing by subtracting this minus this. So I have subtracted this minus this. Okay, so I've taken this whole term, and from that I've subtracted this. So effectively it is like this. It is t plus delta t square minus 5 times t plus delta t plus 1. This whole thing minus of t square minus 5t plus 1. This is what I've done in this step. Okay, good. So I think we should be ready for the last part now. Let's come to that. Now, in the last part, we have to find the velocity as a function of time. Okay. And we will see that we could have also done this question going backwards. We could have actually started with the third part, figuring out what is the velocity as a function of time, instantaneous velocity, and from that calculated the displacement between 3 and 4 seconds and calculated the displacement from t to t plus delta t, like that. We could have done that also. Okay. But anyway, let's see how we'll do that. So for that only, you see that to answer your question, Aparna, yes, you can apply differentiation over here, and that would be the absolute proper way of solving this question. Okay. But here, since I haven't covered differentiation in this batch yet, so I will avoid differentiation for the moment. Okay. In a few lectures, I will cover differentiation, and then we will learn this type of question as well as more complex questions, how to do by differentiation method. But here I'll just use a simple thing that if you look at, so for the third part, if you just observe what is given to us as the position, it is given to us as t square minus 5t plus 1. Okay. So according to this, what is the position at t equal to 0? It is plus 1, correct? And what is the position at time t equal to t? It is nothing but t square minus 5t plus 1. So first of all, from this, what is the displacement at time t? Okay. So this is the displacement from time 0 to t. Okay. So this displacement is nothing but again x at time t minus x at 0. So that you can see when you subtract this minus this, it is just t square minus 5t. Okay, so that's the first thing. By subtracting these two terms, you can see your displacement from time 0 to time t is given by this equation t square minus 5t. Now instead of differentiating displacement, which is the calculus way of solving the problem, I'm not going to do that. What I'm going to do here is I'm going to just observe this displacement and conclude something from that. Okay. What kind of function displacement is? It is a quadratic function. So note what is happening here. The displacement is a quadratic function of time. So what does that tell us? That means the acceleration is constant. Therefore, acceleration A is constant. So we know that if initial velocity is given by u and uniform acceleration or constant acceleration is given by E, then what is the formula of displacement as a function of time? Displacement is equal to ut plus half at square. And what is the function of velocity as a function of time? It is u plus at. And you also have the corollary third equation that if you eliminate time between these two, you get the equation v square is equal to u square plus 2s. Okay. So at the moment, let's just say we are not worried about derivation of these equations. In fact, we are going to do the derivation very soon. We just know from our knowledge in physics, we know that whenever our acceleration is constant, the displacement is given as a function like this, the velocity is given as a function like this, and the relationship between velocity and displacement is given by a third function like this. Okay. So now just look at your observation. So that is the thing. Now, because it's a quadratic function, if you ask the question why I have assumed that acceleration is constant, because the equation here is showing me that s is quadratic in time. So I'm using my knowledge in physics कि s quadratic कब होता है जब acceleration constant होता है. That is the connection I'm making. That if acceleration is constant, then displacement has to be quadratic. If acceleration is variable, then displacement will not be quadratic. If acceleration is zero for that matter, then displacement will just be linear in time. It will be just v into t. No, it will not be ut plus half at square. So using that kind of knowledge that I have, that whenever acceleration is constant, the displacement is this type of function. It's got a t square term and it's got a t term. So you can compare with this. This equation has got a t square term, it's got a t term. So that means the acceleration is constant. Okay, so that is the connection we are making. So now comparing this equation with this. Okay, so comparing with the given equation, what are we getting for the initial velocity? We are getting it as -5. Okay, and the unit is in meters per second. And what are we getting as the acceleration? We are getting it as plus, but how much? +2 meters per second square. Because the coefficient of t square is, see what it is, half a. No? So half a is equal to 1. And the coefficient of t is u. So this is coming from the fact that u is equal to -5, okay, directly by comparison, and half a, which is the coefficient of t square, this term is equal to how much? 1. So that's why e is equal to 2. So this is the two important information that we need. Now once you got the information, anything else I require, like velocity as a function of time or velocity as a function of displacement, that we easily get. So that's looking like this. Okay. So you can see that therefore velocity as a function of time, which is u plus at, okay, just becomes over here. Okay. So a common habit of writing velocity as a vector, but so in this particular example, it's 1D motion. So this is -5 plus 2p. This is my velocity as a function of time. If you already know differentiation, you will realize very quickly that if you differentiate that relation was s was equal to t square minus 5t. If you differentiate this, you will get this. Okay. So you can also apply the concept that v is equal to differentiation of s with respect to time. But if you don't know this step of differentiation, then don't worry right now. We will learn this very, very soon. Okay. This step is called differentiation. So differentiation is something that will come very soon in our syllabus, but as of now, I'm steering clear of it. Okay? If you know from beforehand from some other course, then it's well and good. You can use that. It's no problem. Okay? So I will just minimize this for a moment and show you how we got the velocity, therefore, as a function of time. So all the steps. Alright, people. So this should be pretty simple and easy. Yeah. So again, to come back to this, looking at the equation of x as a function of time. Okay. You can see that you are getting displacement as a function of time as x at time t minus x at t equal to 0. So that's t square minus 5t. And then from the displacement as a function of time, you can understand it being quadratic. It means that your acceleration is constant. Now, because the displacement is a quadratic function of time, we immediately understand that we are dealing with a situation where the acceleration of my body is constant. So given that the acceleration is constant, I can just compare it with the standard equations that s is equal to ut plus half at square, v is equal to u plus at, and v square is equal to u square plus 2as. So that is the method that we are using for solving over here. We are basically using a method of comparison with standard equations. Alright, so Yuvraj, I hope this is clear. Bhumi, to answer your question, you will get the video lecture of this at the end. So if you've joined in late, unfortunately for whatever reason, you can, I know you got locked out or something in between, so don't worry about that. In fact, any of you at some stage because of internet issues or whatever, if you get locked out or some stage the video starts getting this thing stuck and all that, you will get a fully video recorded version of this and you can go through this later. And of course, as you go through it later, if you have any other doubts, you can always contact me. Okay, so that's not an issue at all. So that is the one advantage we have of these online lectures, that you get a video of it later, and you can pause, rewind, redo anything you like, which you cannot do for real life lectures. So anyway, so now I was also telling you how we can do this question backwards. If we were doing this question backwards, I would do it like this: that okay, I got my x was whatever t square minus 5t plus 1. So from this I got my displacement formula as t square minus 5t. So excuse me for a second. Okay, so coming back to this, so my displacement was like this. That was the next way. Okay, and from that I saw that okay, the velocity is becoming 2t minus 5 because I compared this with the standard equation that s is equal to ut plus half at square and v is equal to u plus at. And I saw that by comparison over here, the value of u was minus 5 and the value of a was plus 2. This is what was happening over here. Okay. Now, from this, can I solve the question the other way? That is, find displacement from 3 to 4 seconds. Okay. Or if I ask you something even more interesting. Okay. Now, let's say I also want to calculate distance traveled. Let's add that part to this question. Let's calculate the distance traveled from 2 to 3 seconds. Now, this part you will understand is very tricky because if you go back to what we've done earlier, we had seen that between 2 and 3 seconds, the particle actually turned. And up to 2 seconds, it was going in the negative direction. After 2 seconds, it continued in the negative direction, but somewhere it changed its direction. So it came from minus 5, it went further down to minus something, and then came back to minus 5 at t equal to 3 seconds. So we know that the displacement from 2 to 3 seconds is 0, but that doesn't mean the distance is 0. So this is a little bit tricky. And for this kind of part only, I want to show you how the velocity time graph will help us. Okay. So if I do this problem, instead of using the values like I had done last time, that I had calculated x1, x2, x3 like that, if I just follow the graph, okay, so I say that okay, my displacement versus time is ut plus half at square. So my velocity versus time is u plus at, and that is coming out like this. Now next, let me do something. Let me plot the velocity time graph. Okay. So from this, v is equal to 2t minus 5. Okay. Let us plot the velocity versus time graph. So that is going to be a very interesting relationship we'll see now. Velocity versus time, suppose this is in seconds and this is in meters per second. So you can see that at t equal to 0, what is the value of velocity? It's minus 5. It starts from, let's say, over here at the value minus 5. And thereafter, what is happening? It's having a positive slope. This is a line of the type y equal to mx plus c, where the slope is plus 2. So it's positive. So it should be like this. And the y-intercept is minus 5. So it should intersect the x-axis at the point minus 5. So that means in general, my line should look like this. So this is what the velocity should look like. Okay. Now, obviously, you can understand that at some point of time, the velocity will become 0. And you can see when that is happening. Just put 2t minus 5 as 0. So you can see that velocity is becoming 0 at how much time? At t equal to 5 by 2. So this is 2.5 seconds. Okay. You can see that, for example, at t equal to 1 second, if that is somewhere over here, the velocity would be how much? It would be 2 minus 5. So it would be minus 3. So at t equal to 1 second, the velocity would be minus 3. And you can see see that at t equal to 2 seconds, which might be somewhere here, it will be how much? It will be 4 minus 5, so it will be minus 1. So this is how the velocity is changing with time. You can also see that at 3 seconds, for example, the velocity would have become positive. The velocity will become by now, it will be 6, so it will become plus 1. Then similarly, if you see at 4 seconds, the velocity will become a larger value which is positive. So it will become 8 minus 5, so that is plus 3. So now this graph is giving us very useful information, because what is the use of the velocity time graph? The use of it is that the area under the graph gives us what? It gives us displacement. So let us use this fact now. Let us use the fact that the area under the graph is going to give us displacement to calculate what I've asked you. One is recalculate what we have done in the first part, that is displacement from 3 to 4 seconds. But second is a more tricky thing. Find the distance traveled by the particle from 2 to 3 seconds. I want you to find the distance traveled by the particle from 2 to 3 seconds. Okay? So use this to find the displacement from 3 to 4 seconds. And also use this to find the distance traveled from 2 to 3 seconds. Okay, people. So just try this out, guys. Just note down the graph and try this out. Alright, people, I'm just stopping the share screen for a moment, but please continue working on the question and tell me the answer for that part. The distance traveled. I want the answer for that part. The distance traveled from 2 to 3 seconds. If anybody's got the answer, yes, that seems correct. Good. I've got a couple of replies, and I'm happy with the values you're giving me. So let me just zoom in on the diagram for displacement at that part. Yes, Adinath, that's correct what you just mentioned. So first of all, let me just zoom in on that path where you're seeing the graph a little more closely. Let's look at it. So now let's say the graph was something like this, or I'm just referring to this part. I'm not too worried about the earlier part, so that's why. Okay. So you will see that this is where we had our time when the velocity became 0. So that was 2.5 seconds. 3 seconds was somewhere here, let us say. Okay. And by that logic, 4 seconds will be, let us say, somewhere here. And similarly, let's say 2 seconds is somewhere here. And therefore, yeah, so I'll bring back the graph to machine. Okay. So coming back here, this is our velocity versus time graph. So at 3 seconds, we had seen the velocity was plus 1 meters per second, and at 4 seconds, similarly, the velocity had increased to plus 3 meters per second. Whereas at 2 seconds, it was minus 1, and let's say at 1 second somewhere here, it was minus 3 like that. This is the various things that we had plotted. Okay. So this was time in seconds, this was velocity in meters per second. Now we are interested in two things over here. We are interested in what's happening between 3 and 4. So that is this area. So first of all, very clearly from the graph, you can see that between 3 and 4, the displacement is positive. See, don't confuse this with the fact that the coordinate was negative. It was going from minus 3 to minus 5. Doesn't matter, it was on the other side of the x-axis. But what about the direction of motion? It was along the positive x direction. So the particle between 3 and 4 seconds, it was going from the coordinate minus 5 to minus 3. And your origin is somewhere here. So between that t equal to 3 seconds and 3 equal to 4 seconds, it was here. So you can see its velocity was positive. That is why the velocity is positive over here. And this area, this nothing but represents a displacement from 3 to 4. So we can calculate that area as the area of the trapezium. Okay, so that's one thing we can do here. So if I just minimize this now, so displacement from 3 to 4 seconds is nothing but the area of the trapezium, which I have shown over there. So for the area of trapezium, I'll use the standard formula. It is half into sum of parallel sides, okay, into perpendicular distance between them. So I'm just drawing this trapezium separately over here for you to understand. So this trapezium has this side, let's say A, that is equal to how much? It is this height, so that is how much? It's 1 meter per second. Okay. And this side is the other parallel side B. So its height is how much? It's this value over here. So this value over here, if you follow my cursor, it is nothing but this value. It is 3 meters per second, right? So it's 3 meters per second. And this is the, since this is 90 degrees at the bottom, so this is the perpendicular distance between them. So that is this from 3 to 4. So it is 1 second. So D is 1 second. So substitute that over here. Half into the sum of the parallel sides 1 plus 3 multiplied by the distance between them, which is 1. And this is in meters per second, this is in seconds. So the product will give us meters. So as you can see, you are getting 4 by 2 or 2. And it's on the positive side. So the displacement is positive. You can see that the area is falling on which side? It is falling on the positive side. So it's going to give us 1. So this becomes the answer to our this part. Okay, people. So hope this is clear. Okay. Now I'm coming to the displacement between 1 and 2 seconds. Sorry, between 2 and 3, which is going to be very interesting over here. So the whole problem with calculating distance between 2 and 3 seconds is that in that time interval between 2 and 3, it is turning. So we cannot calculate the displacement directly, the distance directly as magnitude of displacement. No, we have to divide that interval into 2 parts. One where it is traveling in the negative direction, and then one where it's traveling along the positive direction. That is where my velocity time graph comes in very handy. Because from the graph analysis itself, we understand that the particle turn kab kar raha hai. It is turning at 2.5 seconds. How we analyze that? We analyze that from the equation of the velocity time. Velocity time equation kya tha? V was equal to 2t minus 5. So that, from that equation, it was very easy to understand why the particle is turning its direction at 2.5 seconds. Because the velocity time graph straight line is crossing the x-axis, that is the time axis at which point of time? At time equal to 2.5 seconds. So that is what made life easy over here. Yes, Dhruv, Adinath, your answers appear to be correct. I will just verify the numerical value exactly. Okay, so now let us come to this part where we are calculating the distance traveled from 3 to 4 seconds. Okay, so next thing, we want to find distance D. Sorry, not from 3 to 4, but from t equal to 2 to 3 seconds. Okay. Now the problem with this interval is that we know the body takes a turn. In fact, it's a U-turn in between. Okay. So that is why the distance traveled from 2 to 3 will not come by just considering it as the magnitude of displacement from 2 to 3. This will not be the case. Okay, so that is the issue. So first of all, we need to find out when it turns. So that is where your velocity time graph comes in very handy. Now your velocity time graph is now showing you when it turns, because you can see that your velocity time graph is such that at this time of 2.5 seconds, you can see for t greater than 2.5, velocity is positive. For t less than 2.5 seconds, velocity is negative. So that means that the particle or the body or whatever turns at t equal to 2.5. And remember how we had got the time as 2.5, because we knew the velocity was given by this equation, 2t minus 5. So we just put the value of b as 0. So we know this time is this. Okay. So now we are looking at this interval, this whole interval. So sorry, from 2. So we can see that from 2 to 2.5, it is having this negative displacement. Whereas from 2.5 to 3, it is having this positive displacement. So literally what is happening is on the x, so this was velocity versus time graph. But if you compare the same thing versus with respect to the timeline now, what is happening is the particle was here at x equal to minus 3 at t equal to this thing. Sorry, it was at x equal to minus 5. It was at x equal to -5 at t equal to 2 seconds. Then it went in this direction. It then took a U-turn and came back. And then came back again here at t equal to 3 seconds. So this was the issue. So now we know that when exactly it takes taking the U-turn. It's taking the U-turn now. We know that that time is 2.5 seconds. This time over here is 2.5 seconds. So now all we have to do is calculate the negative displacement from here to here. That is from 2 to 2.5. And then calculate the positive displacement from 2.5 to 2, which to 3, sorry, which is this one. And we know the total displacement. Okay? So once we know that the turning is happening at 2.5 seconds, we can see that the distance traveled from 2 to 3 seconds, we can write as the distance traveled from 2 to 2.5 plus the distance traveled from 2.5 to 3. So why we are breaking this up is because we'll have to calculate this as separate modulus of displacement. This is modulus of displacement from 2 to 2.5 plus modulus of displacement from 2.5 to 3. Okay. Now you come back to the diagram and you understand the modulus of displacement, how we get. So this velocity we had seen was -1 and this velocity we had seen was +1. So this area will come out to be how much? Half base into height. And this area will come out to be how much? Half base into height. So each of those areas are the same actually. They are symmetrical. So this value, the displacement actually is negative of that area. Okay, so it is negative of area of that triangle 1. This one was triangle 1. And this one is positive of the area of triangle 2, let's say, in my diagram. And this one is triangle 1. This one is triangle 1. And this one is triangle 2. So you will see that their areas are like this. Half of base, which was 0.5 seconds, into height, which was 1 meter per second. And again, this one is also the same, but it's just coming with a plus sign. Okay. So you can see that from 2 to 2.5 seconds, the particle is actually displaced by how much? 0.25 meters backwards. And then in the next 0.5 seconds, that is from 2.5 to 3, it's again come forwards by that much. That's why its net displacement was 0. But we are not interested in net displacement. We are interested in distance traveled. So that is 0.25 plus 0.25. Okay. So that is 0.5 meters. So that should be the distance traveled from 2 to 3 seconds. 2 to 2.5, it is 0.25 meters. And again 2.5 to 3, it is 0.25 meters. And that's why the net distance traveled is so much. Okay. So this is the approach of solving a problem like this, where you can see that if we have that tricky situation that your velocity is changing direction from negative to positive, then we can always calculate the distance traveled very easily by using the velocity time graph. In the velocity time graph, you just understand that जहाँ पे velocity negative side में है, वहाँ पे area under the curve is giving you a negative displacement. और जहाँ पे velocity positive side में है, the area under the curve is giving you a positive displacement. Now, when you have to calculate total distance, you have to just calculate the magnitude of this displacement, which is negative, plus the magnitude of this displacement, which is positive. It just becomes a matter of individually calculating those areas and then adding their magnitudes instead of adding them with algebraic sign. Okay, so hope this point is clear to all of you. Just go through this section first, and then I'll scroll down below also. Okay, so this is the second part. We want to calculate the distance from 2 to 3 seconds. So the problem is this, that we know that the particle is changing direction in between. So we cannot write the distance directly as magnitude of displacement. Instead, what we have to do is we have to divide that interval of time into 2 sections. One section where it's going negative, then one section where it's going positive. So how do we figure out where it's going negative, how it's going, where it's going positive? That's where the graph comes in. That's where our understanding of the velocity time graph comes in. So people, hope this is clear. I will just leave you with a few seconds to go through this graph, this part, and then we'll come to the section below. people. So just taking you to the final steps below. All right. So I think the final part should be clear from this now. So that's an alternate sort of approach that we can use using the velocity time graph. Okay. In fact, through this only, we are actually learning a lot of things about motion along a straight line with uniform acceleration or uniform deceleration, which is more of what we are going to discuss today. Now, again, the seventh question I think will be easy enough for you. So I will be sending the answer keys, and from that you can verify all this. So I'm now moving on to the next sort of application and next sort of theory in the part that we're studying. So next up, we are going to concentrate on kinematics along a straight line, but with uniform acceleration. So next, we're going to concentrate on this section of kinematics where we are looking at uniformly accelerated motion along a straight line. Okay. So first of all, we are going to understand the three equations: V equal to U plus AT, S is equal to UT plus half AT square, and V square is equal to U square plus 2S. But we are going to understand them in context of what is the logic behind these equations. Okay? So what is happening here is that acceleration is uniform or constant. So what that means is our definition of instantaneous acceleration, which was change in velocity upon change in time for a very short interval of time, for delta t being a very small interval of time. And A was what we call instantaneous acceleration. So this was the definition, whereas average acceleration was change in velocity, so that is v minus u divided by time. This was the relation. Now the important thing is that whenever acceleration is constant, okay, so when the instantaneous acceleration is constant or uniform, it implies that the average acceleration will become equal to the instantaneous acceleration. Okay, just now try to understand what I mean by this. If I'm moving along a straight line such that my acceleration is never changing, it is always increasing at a uniform rate, the velocity, or the velocity is always decreasing at the uniform rate, then for the entire journey, my average acceleration will be equal to nothing but what the instantaneous acceleration's constant value was. So the moment that happens, we can say that v minus u divided by time, which is the average acceleration, the change in velocity over the total amount of change in time, this becomes the constant. Okay. And that is how we get the relation that v is equal to u plus a. Okay. That is how we get this. Or if you think of this in terms of graph, if you think in terms of this as graph, we'll see that if So before you write all this down, let me explain what I mean over here. So suppose we are making a displacement versus time graph. And in one case, my displacement versus time graph looks like this. So what this is showing me? This is showing non-uniform. Oh, sorry, I'm not talking about displacement versus time. I'm talking about velocity versus time. Just excuse me for a moment. So I'm talking about, suppose, velocity versus time graph. So this is telling me what, that if you look at the slope of the graph at any point of time, or if I want to find out what we call the instantaneous velocity at any point of time, what is that? It is equal to the slope of the graph. It's like this, like this, like this, like this. So all the time the slope is changing. So when I convert this to a velocity versus time graph, how is that looking like? So if my displacement versus time graph does not have a fixed slope, or does not have even a fixed curvature, so you can see that what that tells me about the velocity versus time graph is that the velocity is also increasing and decreasing non-uniformly. The velocity is doing something like this. Doing something like this. So you can see that at a certain instant of time, what is the instantaneous acceleration? Now, if we want to find the instantaneous acceleration, so to do that, we have to take a very small interval of time, like this, t to t plus delta t. And during that time, we can see that the velocity has changed from v to this value, v plus delta v. And then what we have to do is we have to join these 2 points with a straight line, like this. And the slope of that straight line, so this is will become the acceleration. So the instantaneous acceleration will become delta v by delta t. So further, what you can understand is that in this graph, since this is changing according to a curve, if you calculate the instantaneous acceleration for this small interval of time and then again recalculate it for this interval of time, you can see it's different. This line here has a different slope compared to this line over here. Or you plot it at some other point of time here. So line joining those two is a line length. So the instantaneous value of acceleration here is, let's say, A2. Here it is, let's say, A1. And here it is, let's say, A3. You can see they are not all equal. A1 is not equal to A2, is not equal to A3. So this is a case of what? This is a case of variable acceleration. So this is not what we want. What we want over here is that the acceleration should be uniform. So on the other hand, if we are now talking about a situation where the acceleration is uniform, then what should our graph look like? It should look like a graph where the slope of the velocity time thing is always constant. So when I calculate delta v by delta t for any 2 points, it should give me the same slope. That is what I mean by it. Okay? So now if I'm plotting a uniformly accelerated motion, so that means the value of A, which is delta v by delta t, should be uniform everywhere. So you'll see that the graph, this graph should be such that I take any 2 points on the black colored line, which is the velocity time graph, and join them with a straight line. That straight line should have the same slope. It should not have 3 different slopes like A1, A2, and A3 over here, the 3 red colored lines. So the conclusion you come to that the velocity versus time graph here has to be which kind of a line? It has to be a straight line. It has to be of this type. Only then it is possible that whether I am calculating the acceleration between this time and this time. So let's say this is t1 and this is t1 plus delta t, or I am plotting between this time and this time. So this is t2 and this is t2 plus delta t, or I am plotting somewhere else. Any 2 points that I take, you can see the slope is the same. So you can see that the acceleration, which is delta v by delta t, is uniform because it is a straight line. So that becomes the integration. Okay? That shows me that whenever acceleration is uniform, velocity versus time should be what kind of graph? It should be a straight line. Okay. Now, if the velocity versus time is a straight line, then it obviously makes sense that its slope is uniform. So No, wherever this line is cutting this x-axis, this is my initial velocity at t equal to 0. And then again, wherever at some general time t, let's say over here, at some general time t, the value of velocity is v. So you can see that this v minus u upon t is nothing but the slope of this straight line, because we are just referencing this point and this point. So the slope of the line can also be written as v minus u by the total time from here to here. Okay. So this time is t, and this time is, this is v minus u. Or it can also be written as this small interval over here, which is delta v by delta t. At any of these 3 points, t1, t2 or t3, if I just make a small interval delta t, that delta v by delta t will also be the same as this. So this is what we mean by saying that whenever my acceleration is uniform, my instantaneous acceleration is equal to the average acceleration, and from that we can see that the instantaneous velocity at some time will be the initial velocity plus that linear acceleration, or that constant linear acceleration multiplied by time. So this is the graphical logic to what we were saying, that whenever acceleration is uniform, it compulsorily means what? That average acceleration will be equal to instantaneous acceleration. This statement that we said, that since my acceleration is, since I'm talking about uniformly accelerated motion, so what that means is that, so since my acceleration is uniform, what that means is that the instantaneous acceleration will always be equal to average acceleration. Okay? The instantaneous acceleration will always be equal to average acceleration. So that further gives me that v is equal to u plus at, or in other words, velocity versus time has to be what kind of graph? It has to be a straight line. This is the first thing, and this is the derivation of the formula that v is equal to u plus a. All right. So I'll just leave this for you for a moment so that you make sure you understand this part here. We'll come to the graphical explanation next. So what is the first learning that we've got from this exercise over here? We've understood that whenever my acceleration is uniform, compulsorily my instantaneous acceleration, that is delta v by delta t for a small delta t, has to be equal to my average acceleration, which is total change in velocity divided by total time, that is v minus u divided by t. All right, people. So hope this is clear. Okay. Now, having said that, instantaneous acceleration is equal to average acceleration. That means the only possibility for velocity time graph is that it has to be a straight line. Because if I have some kind of a motion like this, where displacement is varying like this, so velocity is varying in a random manner like this. It's not varying according to a straight line. So you can see that the slope of delta v by delta t will be different at different points of time. So at this time t1, at this time t2, and this time t3, I'm getting 3 different accelerations. Whereas I want these 3 accelerations to be the same. That means these 3 red lines, which represent the tangent to the curve at these 3 points, they have to actually coincide. So that means compulsorily it cannot be a curve. My VT graph cannot be a curve. It has to be a straight line. So that if I select any 2 points of time in between, the slope has to be the same. So that's where we understand that whenever my acceleration is uniform, compulsorily my V versus T graph has to be what kind of a graph? It has to be a straight line graph. And again, from the straight line, we can derive by using the slope formula y v is equal to u plus v. Right, people? So hope this point is clear. Now, having said this, you will see that in general, there are 4 types of graphs we can get for straight line, okay? Depending on the algebraic sign. So, V versus T graphs, when acceleration is uniform. Okay. Example 1 is something like this, that the initial velocity is positive. Okay. And the acceleration is also positive, let's say. So in this, what will happen? Because the acceleration is in the same direction as the initial velocity, the velocity will increase. So when I draw the straight line graph, it should be a graph where the velocity starts from the value of 10, but it increases with time. So this will look like a graph which has a positive y-intercept because the initial velocity is positive, It will start from a positive value of 10, and thereafter it will go on increasing. It will go on increasing like this. So my straight line graph has to look like this, such that the slope of this straight line has to be equal to 2. So acceleration will be nothing but the slope, and that will be equal to plus 2. So you can see that by the time you come to 1 second, for example, somewhere here, the velocity would have increased to 12. By the time you come to, let's say, 10 seconds over here, the velocity would have increased to 30, because it would have become like this. Because here the formula will become v is equal to 10 plus 2. So you can see it's a straight line which has a positive y-intercept, okay, and it has a positive slope. So the straight line looks like this. Okay. So I think this is pretty self-explanatory. Okay, now next, let us look at an example where they are of opposite sign. So suppose we have a situation where initial velocity is plus 10, okay, but the acceleration is, let us say, minus 4 meters per second. So here what happens, my velocity as a function of time is 10 minus 40. So it's actually wrong to say velocity is all the time decreasing, because after a certain stage the magnitude of velocity will again start increasing. But first it has to come to 0. First the velocity has to come from 10 to 0, and thereafter it will go from 0 to negative values. And as it goes to negative values, again you will see the speed of the particle will be increasing. So here how the velocity time graph will look is that at 0 it is starting from a positive value of plus 10. Okay. But it will have to, from thereafter, it will have to decrease. So it will have to have a negative slope, because the acceleration is negative. It will have to be something like this. So this is what is the meaning of acceleration being minus 4 meters per second square. So it has a negative slope. So for example, you can see that the velocity is decreasing to 6 by the time it is 1 second. Then it is decreasing to 2 by the time it is 2 seconds. Okay. Then again you can see at 2.5 it is becoming 0. Then by the time it's 3 seconds, the velocity would have again increased to minus 2. So from 0 the speed has increased to 2, but the direction has become reversed. Then by the time it's 4 seconds, the velocity here, it would have changed to, so I'll just tidy this up a little. This value will be minus 2. This value will be minus 6. This one. Okay. And similarly, by the time it's 5 seconds, you can see it is minus 10. Like this. So again, this part of the motion from 2.5 seconds onwards, 2.5 seconds onwards, if we see the speed, again it is increasing. But 0 to 2.5 seconds, what is happening? The speed is decreasing. So just because acceleration is negative, we should not jump to the conclusion that we are talking about a decelerated motion, because a decelerated motion is one where the speed is decreasing. But yes, if the velocity is positive and the acceleration is negative, like in this part, between 0 and 2.5 seconds, the velocity is a positive value and the acceleration is negative. So in that part, the motion is decelerated. Whereas in the other part of the journey, the motion becomes accelerated. Okay. So here, what is happening? 0 to 2.5 seconds, we will say that it is what we call a decelerated motion, because the speed is decreasing. But again, 2.5 seconds onwards, it's an accelerated motion. And that too uniformly accelerated. And earlier it was uniformly decelerated. Okay. So I will just leave you with a moment to go through this graph from the example carefully. So these are the primary two examples where initial velocity is positive, but the uniform acceleration is either in the same direction, so it's positive, or it's in the opposite direction, so it is negative. So fairly self-explanatory. Now the other two cases you will see are nothing complicated. They are just like a mirror image of these two. So I'm going to just put them together at one place. Okay. So example 3 is, suppose my initial velocity is negative. So let's say it's minus 20, but my acceleration is positive. It's plus 4 meters per second. So this is like the one, that question we did a little while back. So here what is happening is your velocity time graph will look like this. So it will start from a negative value, but it will become 0 after time. So again, you can see over here that because it's starting from the value of minus 20 and it's having a slope, which is the acceleration, which is plus 4. So this time when it becomes 0 will become 5 seconds. And then again, you will see by symmetry at 10 seconds, it would have come to a value, the velocity would have come to a value over here of plus 20. So just like that question, you'll see between 0 and 5 seconds, it has a negative displacement. Between 5 and 10 seconds, it has an equal but opposite amount of positive displacement. So actually between 0 and 10 seconds, this is what it's doing. It's starting from 0 here, coming like this, then at t equal to 5 seconds, it's turning, and then coming back over here at t equal to 10 seconds. This is what is happening over here. That's why the net displacement from 0 to 10 seconds is 0. Whereas if we are to look at the fourth and final case, which you would have guessed by now, just for the sake of completeness that we are finishing this. Okay. Example 4, if initial velocity is also negative and the uniform acceleration is also negative. So let's say this is minus 10 meters per second and this is minus 2 meters per second square. So it's just like the first graph we had drawn in this series for the positive A and the positive U, but it's a mirror image of that. Okay. So now this will actually look like this. The velocity will never become positive here. It will always remain negative only because the acceleration is negative and the initial velocity is also negative. So you'll see that this graph will just look something like this. Starting from a value of minus 10, and let's say by the time it's 10 seconds, for example, it would have become minus 10 minus of 2 into 10. So it would have become minus 30. Similarly, by the time it's gone to 15 seconds, this would have become minus 10 minus of 30. So it would have become minus 40. So like this, it has a negative slope, which is the value of acceleration, which is minus 2. So in general, you can say that if you want to be very descriptive about what are the different types of graphs you can get depending on algebraic sign when your acceleration is constant. So these are the 4 types of graphs you can get. But out of the 4, actually 2 are, I mean, you can club them together like 2. That either U and A have same sign or U and A have opposite sign. So when they have same sign, it looks like, you know, the quantity is, the magnitude is increasing all the way. So it's a uniform acceleration. Whereas when they have opposite sign, then it initially decelerates and then again accelerates. So this is about velocity versus time. Okay. So I think they should be fairly clear. So I'm not giving you too much time with this because you'll get the notes also. Now let's move on to the next part of our analysis, where we now have to understand displacement. So we have got so far where we have understood that if A is constant, then my V is equal to U plus AT. Now next thing is I want to find displacement. So for displacement, I'll use the concept that displacement is the area under the velocity versus time graph. Okay. So let's take the simplest case of these graphs where U and A are both positive, and let's derive the formula for it. So let's take a case like this, where something like this is happening. It's starting from a positive velocity and its acceleration is positive. So this is a case where in this example, we are taking U as positive and A also as positive. So let's see what is the formula we get. So we want to find the displacement up to this time. when the velocity has become this value v. So what is the displacement? Is this area. So this area is the displacement from time 0 to t. So what is the trick for the area we'll use? What we have done earlier is the area of the trapezium. So it is area of trapezium. So that is half sum of parallel sides multiplied by perpendicular distance. Okay. So one step further, you can see what are the parallel sides over here. The parallel sides are this side, which is u, and this height over here, this one, which is v. And what is the perpendicular distance between them is this one, which is the time t. So one way to write the displacement is that it is p by 2 into u plus v. But remember, we wanted to find the displacement as a function of time, and here v is also a function of time. So what we understand is that here we will have to now substitute from the first equation, which we derived, v as u plus at. So the moment you do that, you come to your classic equation that s is equal to ut plus half at. So just substitute this over here, u plus v, which itself is u plus at. Okay. And now I leave it to you guys to complete the steps here and show that this equation will give us ut plus half at square, which is going to be labeled as our second equation of motion for uniform acceleration. Okay. Albeit I have demonstrated with the first type of graph, where what was happening, my u and a were both positive. So very soon I will demonstrate for the second type of graph also, where u and a are of opposite sign, and you will see that it works both ways. Okay. But before that, just take a few seconds to go through this and understand this carefully. Right. So now you might say that this kind of becomes a little bit sticky when we have the graph which is falling like this. How are we going to show that the displacement is like that? So I'm going to take you through an example also to that to understand. And you see how maths works in a wonderful way, and it takes care of things like algebraic sign and all. Okay. So let us just verify this with an example like this. Let's take initial velocity as plus 20 meters per second. And let's take acceleration as, let us say, minus 2 meters per second square. Now I want you to find displacement at t equal to 5 seconds, okay, and t equal to 15 seconds. Now to verify what I have done over here, I want you to do this calculation by using, in the first case, formula method. Just use the formula s is equal to ut plus half at square. And in the second case, for both these parts, I also want you to find by, okay, and also by the graph method. And that's where I'll show you that how the graph takes care of sign very nicely. Okay. So graph method is that the displacement is area under velocity time graph. So for that, you will have to draw the velocity time graph a little carefully and understand how to calculate the area under that. Okay. So this kind of practice in graphs and area under the graph and all this will go a very long way in understanding calculus also when we come to that later. Okay. Which is why I'm emphasizing a lot on this over here. Okay. We're going to do a lot of problems based on graphs. Today we are seeing linear graphs. In the next lecture, we will start looking at quadratic graphs. And for example, in my first lecture, you remember that I did quite a complicated analysis of quadratic functions and how to get their roots and how to get the condition for discriminant to be negative and things like that. So all those type of analysis I'll start explaining in a lot of detail now. Like after today's lecture, you will not have any difficulty with linear graphs. So like that, at a certain stage, you will not have any difficulty with quadratic graphs or graphs of quadratic functions. So the idea is through the kinematics, we are going to learn a lot of mathematical tricks also over here. So just try this out, people, by both the methods. Okay. I will be waiting for your answers. Yeah, so I have already started getting some answers and I'll verify that in a moment. Yeah, good. Aparna, your answer seems to be correct. For the first part, right, you calculated for 5 seconds. Anyone else so far? Yes, Yuvraj, Adinath, correct. Bhagyeshi, correct. Yes, Devanji, correct. Second part, Yuvraj, you have to be a little careful. I'm asking for the displacement, okay, not the distance. Just make sure that what you've calculated is the displacement and not the distance. Okay, I'll verify the answer. Don't worry. But okay, so let me start by doing both the parts by formula method. So if I were to just use the formula method, so I have taken u as plus 20 meters per second, and the acceleration as minus, how much was it, 5 or 4? Sorry, minus 2 meters per second. So my displacement as a function of time will be ut plus half at square, so that it becomes this. Okay, this will be it. So my displacement in the first part, okay, by formula method. So this is everything I'm doing by formula method. So my displacement for the first 5 seconds and then the first 15 seconds. So 20 into 5 minus 5 square. So you see that the displacement will come out to be plus 75 meters. This is in 5 seconds. Similarly, for the second part, I'm taking 15 seconds. So it will be 20 into 15 minus 15 square. So that is 300 minus 225. Correct? So that should be plus 75 meters again. Okay. So it's very interesting. Why in 15 seconds the displacement is the same thing as the value in 5 seconds? Because in between is going to be turning. Now let me understand the same thing by graph method. Okay, so let's, in the B part, let's make the velocity time graph. And from that, let us understand how we are getting the displacement. So U is plus 20, acceleration is minus 2. So velocity will become 20 minus 2t. So this is the graph that I have to plot. So let's get down to doing that first. So let's say this is time in seconds. Now my graph will look like a straight line with a positive y-intercept of 20 and a negative slope of 2. So it will basically look like some kind of graph like this. I'm not really concerned with how much time, so it's just assume the graph is just going on. Okay, so anyway, so this value is how much? It is 20. Okay, and then this value of time should be how much? So you can see from here, velocity is 0 at t equal to how much? 10 seconds. So that's where you know that this 15-second business is very critical. Okay, so 15 is somewhere here, 5 is somewhere here like this. You can see that at 5, the velocity is 20 minus 2 into 5, so it's plus 10. Whereas at 15, you will see the velocity will become how much? 20 minus 2 into 15, so that's 20 minus 30, so it will become minus 20. So now you can almost understand from the graph why you are getting the answer this way, because you can see whatever displacement is happening between 5 and 10 seconds is positive of this triangle, and then between 10 and 15 seconds is positive of this triangle. So whatever displacement he had along the positive direction from 5 to 10, he came back that much from 10 to 15. So from 0 to 15, his net displacement is actually going to be the same as 0 to 5. That is that. Okay. So here, if I'm calculating, let's say the first part I'm calculating the displacement from 0 to 5 seconds. So that should be this area. It should be this area. So it should be positive of, because it's on the positive side, that trapezium's area. So half of sum of parallel sides. So this side you can see is 20 and this side you can see is 10 into the distance between them, which is this distance over here, this perpendicular distance. So that is 5. So as you can see, this is coming out to be plus 75. Okay. But now when I want to calculate the second part, okay, so this was the first part by the A method, I mean by the B method, whatever. Now when I want to calculate, select some unique kind of color. Okay. So I want to calculate the displacement from 0 to 15 seconds. Okay. So if you see this area now, okay, and then also this area. So this will be the displacement from 0 to 5 plus the displacement from 5 to 10 plus the displacement from 10 to 15. If I break it in 3 parts like this, okay. So this part you can already see is this. Okay. So this gets substituted here. So this is 75. But what about the second part? It is coming as this triangle's area. So that's half of base into height. But actually you don't need to calculate because you can see this and this will cancel. But just for the sake of argument, I'm calculating. So it's half of 10 into 5, okay, plus the displacement in this part. Now the displacement in this part will be negative of the area. Why it will be negative of the area? Because here the displacement is negative because velocity is negative. So that is why the displacement from 10 to 15 is negative of the area of that line. Okay. So it is negative of that half into 10 into 5. So that's why actually with the just a symmetry understanding, I could have seen that I don't even need the values here. I can see that this one and this one will cancel each other, and ultimately you will get it as plus 75 meters. So this is as far as the displacement is concerned from 0 to 50. Now I could also ask you a third part, that find the distance from 0 to 50. And that is where you will see your graph comes in extremely handy, because without the graph, you're a little clueless about where to take modulus of displacement, where to take same thing as displacement, where the displacement is becoming negative, where it's positive. So that's where the graph method comes in very, very handy for us. And that is why we have to get a lot of experience in handling these graphs. In all chapters in physics in future also, you'll see graphical analysis always helps us in understanding problems in a more technical way. Okay, so hope the calculation up to here is clear. And if it is, then just work on this part now. The third part of the question, let's say. You have to find the total distance traveled from 0 to 15 seconds. So those who have worked out this part by both the methods, just work out the third question. Yeah, Yuvraj, I will turn to the formula in just a moment. Okay, just finish this graph part first. In case you haven't written down the formula part, then I'll just turn to it in a minute. Right, so I'm waiting for the answer for the third part, in case you already started working on it. Okay, so continue working on the third part for the benefit of anybody who has missed out writing the formula based approach. I'm just yes, Dhruv, that is correct. Aparna, you're also correct. Good, very good. So 125 meters is the correct value of total distance traveled. So you have to see that when you're calculating total distance, just that last part of 10 to 15 seconds, you have to just put the modulus, because the displacement is negative in that part. So you have to just count that without the negative sign. And between 0 and 10, of course, is positive displacement. So okay, so that is where you will again appreciate how much the graph helps us. So I'm coming to the third part now. So in the third part, I want to calculate distance from 0 to 15 seconds. But I understand that at t equal to 10 seconds, velocity switches from positive to negative. So the direction reverses. So that's where I have to be mindful of the fact that therefore my displacement, my distance will become displacement from 0 to 10 seconds plus magnitude of displacement from 10 to 15. Because this is a negative displacement. So this one we had seen earlier was 75 plus 25, a trapezium plus triangle. But this one will now become mod of that minus 25. So that's why the total distance traveled will be 125 meters. Okay. So this is again in correlation to the graph earlier and in correlation to these calculations which I have done here. So, these three values, they just come in with mod. So it is mod 75 plus mod 25 plus mod of minus 25. So that's why instead of plus 75, with the mods, it just comes out to be 125. Right. So this is the story about the second equation of motion and how to use it. Now, quickly as we wind up, we'll also understand the third equation of motion and how to derive it. So for uniformly accelerated motion, we've seen that we've seen that v is equal to u plus at, which is giving you velocity as a function of time. Okay, because u and a are constants, remember. U is the initial velocity, so it's just a value, and a is a constant. It's the velocity which is changing with time. So it's velocity as a function of time, and it's a straight line graph. Like this. Okay, now the second equation is displacement as a function of time. So the second equation gives us displacement as a function of time. And in the next lecture, we'll see in a lot of detail how that displacement graph looks like. It looks like a parabolic curve. So for example, if you talk about initial velocity positive and acceleration positive, you'll see it like this. This is a parabolic curve with u positive and a also positive. You'll see if it's having a negative, then it will be a different type of parabola. So we are coming to all this in the next lecture. So don't worry about this. Okay. But now what we want is next, okay, we want to find a relation of the instantaneous velocity in terms of the instantaneous displacement s and not in terms of t. I don't want v in terms of t, I want v in terms of s. So this is just an algebraic operation. There's no concept or logic involved. We're just going to eliminate the time between the two equations and get the relation between v and s. So you can see v is in terms of t and s is in terms of t. If we use the two equations to eliminate the variable of time, then we will get what we're looking for, which is the relation between v and s. So from equation 1, you can write the time as v minus u upon a. And now you can substitute this relation in equation 2. So that will accomplish the task. So next, you substitute this in the second relation. So in the second relation, your s is equal to ut. So t के जगह क्या आ जाएगा? v minus u upon a plus half at square. So that is square. Okay. So we just simplify this a little bit. It's quite easy to show that this will give us v square is equal to u square plus 2as. So just take v minus u common over here. You can see the first term is just giving us, in fact, you can take by a also common. So the first term is giving us u. In the second term, you see when you open this, it's a upon a square. So it's again 1 by a in the denominator, which I've taken outside. So what I'm left with is v minus u, the whole thing divided by 2. Okay, and then just solve this a little bit further, and we'll get what we have. So v minus u upon a into 2u plus v minus u by 2. Okay. For the next step, that will give us so use that standard formula, a minus b into a plus b is a square minus b square. So v square minus u square upon 2, and this is nothing but s. So now cross multiply and invert this relation. So you get v square is equal to u square plus 2as, which is the all important third equation of motion. But in a sense, it's like a corollary. It's not really some new information. It is just about mathematics that we are eliminating one variable from equation 1 and 2. That is the variable of time, and relating the other two. It's a very useful equation in terms of solving, okay, but it's not really any new information in terms of physics. So hope this part is clear, people. Okay. Right. So this brings this lecture to a conclusion. Okay. And that's it for today for us. Okay. So I'll stop the recording first.